Thank you for attending this webinar with Tracey Smith. My name is Pat Bono, President of New York Bee Wellness, which is an independent, educational, grassroots, charitable 501c3 non-membership organization. Its mission is to educate small-scale, sideliner, and beginning beekeepers. We do have a YouTube site with past in-person and online presentations. New York Bee Wellness also sends out newsletters several times a year, and we conduct statewide surveys twice a year for non-migratory beekeepers in New York State. Welcome, Tracey. Glad to have you present. Thank you.
Thanks, Pat. Uh, so I wanted to talk tonight about queen failure after shipping and my curiosity about whether humidity or maybe dehydration could be playing a role in why we see early queen failures after shipping sometimes. And so just a bit about me, first of all. I started beekeeping back in 2008 while I was living in Alaska. And then I'm from Alberta, though, in Canada. And I learned while I was beekeeping in Alaska that Alberta is a huge beekeeping area of the world. And so I moved back to my home province to learn more about beekeeping. So in 2010, I started my own beekeeping company. I started with 2 hives, packages, all new equipment. And the next year, I got 5 colonies. So I had 7 hives, managed to get 300 pounds of honey each off of those colonies in my second year. And I didn't have enough friends. And so I started my beekeeping company. And so I ran my company, Beanstalk Honey, up until 2021 during COVID. And at that time, my largest number of colonies ever was about 120. I sold to farmers markets and like small grocery stores and stuff around Edmonton. And then in 2021, I decided I wanted to go back to school and do a PhD in honeybee research. And so what I'm presenting tonight is one part of the research that I was doing while I was at the University of Alberta. I was in Dr. Olav Ruppel's lab there. And so that kind of brings me up to now. I had always, as a beekeeper, I had heard about these high failure rates, or like a lot of queens after being shipped long distances, they're not accepted into colonies. They like are superseded prematurely. I'd always bred my own queens, and so I hadn't experienced it firsthand. And it wasn't until I started as a student at the U of A that I realized how big a problem this maybe is. And I wanted to put a camel here because once you start thinking about it, it's kind of funny. Like we almost think about queens as though they're camels, like they have infinite water in them during shipping. And I don't know where we got that idea from necessarily. So how do I change here? So the problem that, as we see it with shipping queens, is that the queens often fail at surprisingly high rates after they've been shipped. One of the hard things about studying this problem is that the high failures are shipment specific and they're sporadic. And so it's hard to identify like what is going on. A lot of you people probably know that recent research has focused on temperature extremes during shipping and the possibility that those temperature extremes could be damaging sperm. Um, I think this the sperm damage, so that's what it is. It means that recently we have a lot of research on what temperatures are bees being exposed to while they're being shipped, and that proved to be in my favor. Um, and so while I was at the U of A, part of my research was looking at if it's not sperm damage that could be causing these high failure rates, what are other possibilities more broadly. And so I was working on this project that was a large collaborative project where we actually imported 3 different shipments of queens. One shipment from California, one from Quebec, and then one was a local breeder that just lived a couple hours away. And we shipped in 60 queens from each of these different sources. And I was responsible for making all sorts of measurements on them to just measure queen quality in general, to see if maybe it's sperm damage, maybe it's something else, we don't know. And when I was dissecting these queens, there was one shipment we had And the queens looked like this. I don't know how many people have, like, pulled honeybees apart, but this is not a happy looking queen. Apart from the fact that she's now being dissected. She looks maybe like she's dehydrated. And that was really what started me down this course of, like, are the queens just getting dehydrated? And it was just the one shipment, probably out of the 60, it was maybe 10. So a pretty high proportion. Uh, so I developed this little side project that we're talking about tonight to see if maybe they're getting dehydrated in shipping. So just some background here. This is a study from Quebec that came out in 2020 that I can demonstrate a point with well. So with this study, every single one of these box and whisker plots is a different shipment of queens. And they put temperature loggers and humidity loggers into these shipments so that they could just see what temperatures and humidities are queens being exposed to during shipping. The idea with the sperm and damage hypothesis is that if queens are exposed to temperatures that are quite high, like say 38, 40 degrees, or if they're exposed to very low temperatures, the queen might live, but her sperm has been damaged. And so you look at the queen after she's been exposed to these high temperatures and you think she's fine, but her sperm has been like irrevocably damaged, and that is what ultimately causes her failure. And so this study was looking at, well, what temperatures are queens exposed to during shipping? And they found of these 23 shipments, none were really exposed to problematic temperatures. And so they thought, well, maybe the temperature hypothesis, it's not that common that they're exposed to those temperatures. And other studies have found this as well. It's just, this is one of the unusual studies that includes relative humidity. So I thought, and then I should add, there's other studies that have shown that, and this is Dave Tarpey's work, that queens often fail when they've been held at extended periods of time during shipping at 32 degrees Celsius, or in that window, like 32 to 34 degrees Celsius, which is weird that extended exposure at those temperatures is associated with higher failure rates, because those are the temperatures that a queen would experience in the colony. And so I thought, okay, so we'll take 32 degrees based on their findings. We know queens tend to fail at those temperatures. They're exposed to that during shipping. And then I wanted to look at, though, well, what if the relative humidity is really low, you're going to increase the probability that they're getting dehydrated, right? It's called the vapor pressure deficit. And as the air becomes drier, we're going to lose more moisture to the air. And so I thought maybe it's actually a vapor pressure deficit that causes dehydration in some shipments. And so I picked, for reasons I won't go into, I picked this cutoff sort of like 30% relative humidity. It's loosely based on some other calculations I did. And you can see there are some shipments that had, like, they were really dry during shipping. And so if we look at what shipments had low relative humidity but high temperature, and we do see that happening sometimes now. And so that's where, like, maybe there's something to this now, right? And then you also have, and this is a quote from one of the Dave Tarpey papers, where they found that because the queens were failing at around 32 degrees, like when they're exposed to 32 degrees for a long time during shipping, the high failure rates of queens following package installation in this case are due to other causes. And so I'm wondering, maybe humidity is one of these other causes. So that's my question. Does a high vapor pressure deficit during shipping contribute to early queen failure? And if it does, maybe we can just provide them with water. If they're getting dehydrated, if we just give them some water to drink, maybe that will decrease early queen failures after shipping. And for anyone who has looked into like how to measure dehydration, it becomes a surprisingly complicated question. And so once I started reading more about physiological responses to low water intake, I started thinking I should look at the body composition of the queens to see if maybe something is weird about the body composition that we can't pick up on but maybe it's something about their body composition that's causing these failures down the road. And maybe by looking at body composition, I can get at some kind of actual measure of whether they're dehydrated or not. I was really fortunate at the U of A. There's this machine called an echo MRI that can measure body composition. I think there's only two machines like this in Canada, and one of them happened to be owned by a hobbyist beekeeper that I knew. And it's in a biomedical research facility at the University of Alberta Hospital. And she was great. She let me use this piece of equipment. It got into a larger topic that I was interested in when I was working on my PhD, and that was how environmental conditions, such as drought, are they having some kind of impact on honeybee body composition? And then, as we're talking about tonight, does that play a role then in queen acceptance? Or I was kind of interested in the parasites aspect with varroa mites, just trying to get I was really interested in like environmental aspects of what could be causing varroa mite populations to be like varroa mite population growth to be so extreme in some years and then in other years are not really much of a problem. Is there an environmental aspect to that? It's kind of trying to build a model, like a conceptual model here. And so that's where I was interested in body composition as well, kind of going down that road. So I'll talk about vapor pressure deficits for a moment here, I believe, and kind of like desiccation resistance in insects. And then we'll talk about like water intake and what low water intake can do to organisms, like sort of physiologically. And then I'll talk a bit about this body composition. Um, so in terms of whether like how desiccation resistant insect is, it hasn't really been studied very much in honeybees at all. It has been studied in ants quite a bit, because ants tend to live in like deserts or rainforest canopies or the understory of the rainforest. This like really extreme set of environmental conditions where you have high vapor pressure deficits and much lower vapor pressure deficits. And so you can see all these different people have studied what is the desiccation resistance of ants. Something everybody agrees on is that the larger body mass an ant has, that's associated with increased desiccation resistance. So we would assume here, if it's the same, that larger body mass queens might have increased desiccation resistance. And then in terms of water intake, again, we haven't, from a physiological perspective or a metabolic perspective, haven't really studied this in honeybees. We have studied it in humans. The human research, I'm not a doctor, it's a little bit overwhelming, but I can say that low water intake in humans is associated with a number of like metabolic diseases, and obesity, uh, which is a really interesting line of research to go down if one is ever interested to learn more about that. And I'll just explain it a little bit here. So there's a number of studies. This is just three that I found, but it's fairly, there are many, many more studies that have shown this as well. That as an adolescent, a child, a human, a person, an adult, as water intake increases, so this is just like daily the amount of water that you drink, as people on average drink more water, those higher water consumers will have greater lean mass and lower fat content. And so the people who are chronically like kind of underhydrated, they tend to have higher fat and lower lean mass. So there's some, and again, I'm not a physiologist, but there are physiological explanations for like increased water intake increases lipolysis, which increases metabolism. You know, there are physiological reasons behind these associations. There's a few different ones, has to do with hormones, not going into it, but it is a known phenomena here. I think it's why doctors are always telling us like drink more water. So the idea here is like, do honeybees have the same response? These are adaptive responses to, like, in a low water environment, you accumulate more fat. And when your body has all the water it needs plus more, you'll have more lean mass and lower fat. And so do we see the same thing in honeybees? Will we see this pattern? And that's what I can get at with by measuring their body composition, right? So this is, I should just point out, this is a different way of thinking about a lot of honeybee research. Usually we're used to thinking about vitellogenin in bees. And in this case, like, how does vitellogenin fit into like the fat lean mass ratio? And it's hard to say because the molecule of vitellogenin actually contains some fat and some not fat. And it's hard to, it doesn't track well. So these aren't really measures of vitellogenin. You have to like actually kind of think about it a different way, and just get used to these measures instead. Uh, so how we measure body composition, again, this echo MRI here hasn't been used in honeybees before, but it's been used in all sorts of other organisms, including cockroaches, lobsters, crayfish, birds. It was actually a study on birds that I read when they were looking at long distance migration and like the dehydration status of birds when they're flying very long distances and how they use fat and muscle mass to maintain hydration status during the migration. That's what was another informative article in this line of research for me. It's been used on bats and then mice, like the lab that I was in, they were doing mouse research with this machine. So the way it works, it's magnetic resonance. And so there's a little tube at the top here. You put the bees or your tissue sample in this tube, and then it'll measure the total water content, the free water, the fat, and the lean mass of the organism. And it'll give you a quantitative readout on this screen. And so it's not imaging, it's actually, it's called like quantitative magnetic resonance because it's giving you a quantitative readout instead of an image, but it's the same technology. And then just a word about what we do know about water intake in honeybees, based on these papers, plus I'm sure there's other ones, is that honeybees do need additional water whenever their food is more concentrated than a 1-to-1 sugar syrup. And so when we think 1-to-1 sugar syrup, that's like 50% water. And honey is what, like, depending on where you are, like 15 to 18%, hopefully not 20% water. And so honey alone does not provide enough water for bees. They need an additional water source. And then the lifespan of caged workers in labs, we know that that's extended if they're provided water in addition to 1-to-1 sugar syrup. And so bees, like, they need more water than we forget that bees need water. We think somehow that they like absorb it from the air or something, which some insects do, but bees don't. Um, and so when we think about situations where bees may not have access to adequate water, it's often the transportation. So these are some situations I could think of, like long distance migratory trucking when they only have access to honey. That could be hard on them depending on the distance and the temperatures and the humidity, potentially. Um, Packages, maybe as well. And then what I'm interested in here is queens during shipping. Because this fondant that we put in here, the queen candy, is uh, not 1-to-1 sugar syrup, if that makes sense. That is a low moisture content compared to what bees need for their water source. So this is the experimental design that I made to try and test these ideas. So I was interested in this vapor pressure deficit idea of maybe it's 32 degrees, but if it's 32 degrees during shipping and really dry, like 30% relative humidity, maybe that's making a difference compared to if it's 32 degrees and say 70% relative humidity. So I set up, those were two factors. And then I also wanted to see maybe we just need to give them water. And so I set it up so that some had water and some had water and some did not have water. So this was the design. I had two, these were actually chicken egg incubators that I put the queens into. And I had two, you'll see actual photos in a minute here too. I had two blocks in each one of these incubators. So one was the dry incubator, 32 degrees and 34% relative humidity. The dry incubator, I gave them water. Dry incubator, no water. And then same thing, I had 32 degrees, 68% relative humidity in my chicken egg incubator. And I provided some water and I didn't give others water. What we would expect here, this, I would expect the queens to be happiest. You know, it's humid, they have water, they've got everything they need, they're gonna be happy. These ones, they've got water, but it's kind of dry, so I'm not really sure. Maybe they'll be okay. This one, humid, so you wouldn't expect them to get dehydrated too quickly. And we haven't given them water, so again, like, I think they'll be okay. And then this one where it's quite hot and dry with no water, this is where I expect the queens will start having issues. So I actually worked with, I don't know if you guys have heard of Saskatraz Queens, but Albert Robertson from Saskatraz Queens, his company name is Meadow Ridge Enterprises. He agreed to work with me on this project and he donated the, I think I had about 55 queens in this study, and he donated them all to me and collaborated with me on this. So on July 12th, I drove all the way out to his place. This is Western Canada. BC, Alberta, Saskatchewan. This is about a 6-hour drive. I drove out there and back in one day. And when I brought the queens home, I took them from their California mini cages that they'd been shipped in. I put them into the JZBZ cages just because they're so much easier to handle when you have to open and shut them a bunch of times. And then I used I'm blanking on what they're called, a soda stream. I used a soda stream with this tube hooked up to it to CO2 them, which is a pretty like do-it-yourself setup. But I was working in a mouse lab buried inside a biomedical building at the university hospital, and so I was not, I didn't have access to like a different setup. And this works really well, actually. There's a paper that tested this protocol for wild pollinators in the field, and they found this was a really nice portable way to CO2 honeybees. So I used it, and it worked. So after I CO2'd them, I weighed them on this really nice scale, and then I put half the bees into the echo MRI to test their body composition. And I left half out because I wanted to make sure that this machine itself, because it hasn't been used on honeybees, I wanted to do a sub experiment to see if this machine would actually kill the bees. I'm not presenting those statistics. I did do them. I did not find any effect of this machine. So I'm pretty confident over a 3-week period after introduction anyways. So I'm pretty confident that we can use this without damaging the bees too much or at all. So that's what I did. I measured them and then I put them inside their treatments here. And so for the treatments, I had to design some way of these bees drinking water. And so I made these little bee watering troughs. I designed them and then 3D printed them. So they fit a block of 12 JZBZ queen cages, and they have access to water this way. So I put one block of 12 in, this is my desiccant. So this is my chicken egg incubator that was the dry environment. I put in one block that had them on a bee watering trough and another one that they didn't have access to water. I did the same thing, but with the humidity jacked up to 68% relative humidity. And then the next, I left them in their treatments. It ended up being for 3 hours. I'll talk about this in a second, but 3 hours. But then I left them on their watering troughs for the rest of the experiment. The next day I went and I moved them all back to the lab. I anesthetized them again and I measured their body composition again and I weighed them again. So I had a before and after the treatment in the incubators of what their body composition looked like. After I did that to them, I drove them back to Saskatchewan again, where Albert Robertson was nice enough to donate 4-frame nucleus colonies to this experiment. He introduced all the queens into these nucleus colonies. He checked them after 3 days for initial acceptance. He released them from the cages if they needed to be released. And then after 3 weeks, he checked for acceptance and then the number of frames of brood and the number of frames of bees. I didn't include any stats here. I was mostly using this to see if I had like damaged the queens by using the quantitative magnetic resonance on them. So the timeline here, just to be clear about this. So I was trying to recreate shipping here. So I was trying to work really quickly because I didn't want these girls, I guess, in transit for too long. And so the entire experiment here was 72 hours from beginning to end, which is, I think, a pretty reasonable amount of time to have queens in shipment for inside queen cages. And so you can see hour 32 to 35 here was when I had them in the incubators, but then hour 32 all the way up till when I returned them, they were hooked up to their watering troughs. I had meant to keep them in this treatment for longer, but after 3 hours, the dry incubator, the bees were making so much noise in there, fanning so hard, that I was worried that they were going to die if I left them in there any longer. I'd meant to leave them in there. I think I was going for 6 to 10 hours or something originally, but I was like, they're not even going to make it. And that wasn't the point of the experiment. You know, I didn't want to be killing the queens. I wanted to be potentially sublethally damaging the queens. And I could tell by their response with their extreme buzzing, agitation, wing fanning that I was verging into territory. They really obviously did not like that incubator. So that was 32 degrees Celsius. Sorry, I just realized I'm speaking in Celsius. You'll have to deal with it because I can't do the translation in my head right now. 32 degrees Celsius and 34% relative humidity. They had troubles with that. So that was the timeline. Observations, in addition to having trouble, like in that incubator, I had actually hoped the incubate. So this is my data logger now, this thing right here. And you can see relative humidity. I had managed to get that relative humidity down to about 25%, which is what I'd initially been aiming for. But then when I put the queens in there, the humidity went up and they maintained 34% for the duration of the experiment, which is maybe why I heard them working so hard in there. I don't know. I don't know if that was intentional or inadvertent just to like metabolic water release, but they did manage to actually control, or they did manage to influence the humidity inside this container, which I think is just something to keep in mind when we're designing queen shipping containers. They can actually elevate the relative humidity in the containers. Another interesting observation from the experiment is that my little bee watering troughs were designed to hold 25 milliliters of water, and after 30 hours, they were completely bone dry empty. And so either through evaporation or actual consumption, the queens out of both incubators, I had 12 cages here, so 12 queens and attendants. That means they went through like 2 milliliters of water each in 30 hours. And like I say, some of that might have just been evaporating, but often people will say, well, I dab my queen cages with water and the queens have enough to drink that way. But I have a hard time imagining dabbing queen cages with water is providing that much water to the queens. Like 2 milliliters is quite a bit. So that was just another interesting observation, just to think about. I just realized I'm not watching the Q&A at all. We'll discuss the Q&A at the end, I think, at this point. So here are the results. Does humidity or supplemental water affect early queen failure rates? And we found that In the Well, basically in the dry environment with no water, 42% of those queens failed within the first 3 weeks of introduction. In the treatments that where they had water and it was dry, only 18% failed. Similarly, where they had no water but it was really humid, only 18% failed. And then in this environment, only one queen failed, 9%. So that's pretty much exactly what we expected. However, the statistics on this, due to the design and the sample size, they're not statistically significant. I built general linear models, GLMs, to test for statistical significance, and this did not come out to be statistically significant. And so it'd be nice to repeat this study, but with a larger sample size, just to see if we see the same results again. However, what did come out to be statistically significant was when I got rid of the 2 humidity treatments and just looked at whether or not I gave them water. This 32% of the queens that were not given water ended up failing within 3 weeks, whereas 14% that were given water failed. It gets a little bit more complicated than that even, because the best model that I built for statistical significance was one where I included body weight too. So I'll show you that slide next. So the queens that failed, so what this slide, the next few slides are all going to look like this, so I'll just take a minute to explain this. So this is looking at the final mass of the queens, and whether or not they had water access. And so these queens did not have water access. These queens did have access to water. And then we're looking at queen outcome here. So the teal ones are the queens that were accepted and did fine in the colonies, whereas the red ones are the ones that failed. And so we're looking at how much mass did they have compared to whether or not they had water. And you can see it was the lighter queens in both treatments that failed. But the significance is that if it were mass alone, we would have expected these ones to fail, and they did not. And so that's where the water supplementation is significant as well. And then if we look, so this is for all my queens. So this is something approaching 50 queens, I believe. This is for just the ones that I scanned. So did the body composition study on, and you can see here the difference is actually, well, again, like it was the lighter queens that failed out of both treatments, but that we would have expected more to fail here than they did if it was body mass alone that was explaining the failure rate, I think is the proper way to put that. So humidity we would need to retest humidity with a larger sample size. But then we get into this body composition stuff. And so now we're just looking at the queens that were accepted. And on the left here, we have the lean mass of the queens, the final lean mass. So this is the second day, what their lean mass was, and then what their fat content was too. And you can see this, remember how I showed you that X of body composition, where like if you don't have high water intake, you'll have higher fat and lower lean mass. And then if you drink a lot of water, you'll have higher lean mass and lower fat. I think it's really neat that that's the pattern we see here. And so that does suggest that they're mounting a physiological, to me, that suggests that they are actually mounting a physiological response to low water or adequate. Well, it's probably low water. They're like, would be the adaptive mechanism for responding to low water situations. And then if we look at the queens that failed, however, so in the red, you can see these queens actually had the same body composition as if they had water, which is really interesting. It means that, to me, again, what this is saying is that the queens that failed somehow didn't respond to the low water situation. And I don't know why that is. I don't know if they had something wrong with them otherwise, or if it was a body mass. I don't know the mechanism behind that, but you can see there was a difference in body composition. This again is not statistically significant. These are very small sample sizes, so hard to get statistical significance. However, what was statistically significant was actually when I looked at the difference. So this is from day 1 before the treatment to day 2. How much did those 2 readings change from one day to the next? And we found that for the queens that were given water, the ones that so that we'll just look again at the ones that were accepted and were fine, so like healthy, good queens. The ones we gave water to actually gained lean mass, whereas the ones we didn't give water to lost lean mass, which is again exactly what you would expect based on like the human research. And the queens that did not have water access did gain fat, and they lost, and the queens that had water access lost fat. Um, these are statistically significant differences with this, where again, there was no difference for the queens that failed. Here, the ones that didn't have water, and the ones that were here, they responded oppositely. Whereas with fat, there was no response at all. So for some reason, the queens with their body composition here, they're not responding to water access the same way that the healthy queens were. Why? I don't know. So that's the summary, that the lighter queens, so the queens with a lower body mass that did not have access to water, failed within 3 weeks at higher rates than the other queens. And so lack of water played a role in queen failure. But I don't know if it caused it, right? Like there could have been something else physiologically wrong with those queens that prevented them from being able to adapt to. I'm saying adapt because I think this is like an evolutionary mechanism for low water situations. And they were unable to execute that adaptive strategy for some reason, if that makes sense. And then the failed queens differed in body composition from the accepted queens. And this is a complicated sentence because there's so many negatives in here, but there was no reduction in lean mass nor an increase in fat in the failed queens that were not provided water. And so all I'm saying there again is, if I can go back, is just these ones, we didn't see a reduction nor an increase in these queens, which is what, yeah. So that's it. I would like to acknowledge some people and organizations here. Albert Robertson from Saskatchewan, Queens was absolutely critical of this experiment. Vivian Butts, she had volunteered queens and was going to do nukes too. So I was going to actually have double the sample size, which would have been great, but I was super sick right after this and had to cancel that part of the experiment. But she was on board with this as well. She's a queen breeder, longtime queen breeder from a multi-generational queen breeding family. They used to have bees down in California, and they would move them up to Alberta every year. They would breed queens down there, move them up here, and then with the border shut, they ended up just being up here. So that was Vivian. Peter Loring-Borst, he helped me with some of the background research for this. Hannah Pierce from the Digital Scholarship Center helped me with the 3D printing. She taught me how to do that. And then Amy Barr was the one at the U of A who happens to be a beekeeper and happened to be able to give me access to the MRI machine to do the work. Part of this project was funded by Project APSM, and I had a grant from the Canadian Honey Council to do this work specifically. So with that, are there any questions? And I can see in the Q&A there might be. So yeah, feel free to put your questions in there. So the first question, and there's one in the chat too. Let me just check the chat first of all. Thank you, Pat. 32 degrees is 89 to 90 Fahrenheit. Uh, so Pete Foster here says, so typically I order package Bs from OHB, Olivieras maybe, on the West Coast and pick them up at Man Lake in West Bar, Pennsylvania after a cross-country trip. They are fed with canned syrup. I find about 30% queen failure replacement after the second to third round of laying. Yeah, so that's really typical, that 30% failure rate. And I think, yeah, I mean, you just heard my hypothesis. Um, I think it's a lack of adequate water. Uh, package bees are more complicated than shipped queens. And so I don't want to extend it too much, especially because they have syrup in the packages. I just think this syrup is still actually not enough water. So, but it would have to be tested for sure, for sure. Um, then so ideally in a cross-country truck containing hundreds of spring packages and cage queens, what should the bee temperature and humidity be? So I think about this now in terms of vapor. Okay, so there's two ways to answer this question. One is that other research has shown, and this is that Dave Tarpey study that I referenced earlier that I can go back to if we want to. They found the lowest rates were in that like 22 degrees Celsius, 24 degrees, anything kind of below 30. The queens had low failure rates. Um, so other research has shown that like moderate temperatures are fine. Uh, if I look at it from a vapor pressure deficit perspective, um, the I would argue the situations where the bees are least likely to start getting dehydrated is anything where the vapor pressure deficit is the same as it is inside the colony or more humid than that. And the vapor pressure deficit, as far as I can tell from um, some other research I did, I think it's usually about 2.2 kilopascals inside the hive. So that's like 32 degrees and about 55% relative humidity. Um, so I guess that's another way of looking at it. If you're going to go up to 32 degrees, you should hope that the relative humidity is about 55% during shipping, based on my kind of theorizing. Actual data shows cooler temperatures are better. How is failure defined? Good question. So we define failure as the queens were all marked. And if we went back and looked in the colony and there was no longer a marked queen in there, then she had failed. And they were just little 4-frame nukes, and so they were pretty easy to find a marked queen or not in there. Well, I'm getting a bit, hang on a second. I've lost my mouse. Okay, did the beekeeper introduce the queens in the nukes in California cages? They introduced the queens into the nukes in the JZBZ cages. And yeah, did you add attendant bees with the queens? Yeah, so I skipped out. There was so much to this study that I skipped out just for the sake of like packaging it into the presentation. And I did do every queen had 5 attendant bees with it. Those 5 attendants, I measured body composition and everything for those attendants too. And so you can actually get into the dynamic of like what was going on with the attendants versus what was going on with the queen. And it gets really, really, really complicated. And so I left all of that out. Hi, Pete. Do you have a specific recommendation for changing the queen shipping equipment? I think that on the one hand, I'm like, everybody should buy the queen shipping container that I just built, the little watering trough. But realistically, I think this study should be repeated before we all go running out to make sure we water the queens during shipping. Or we can, I mean, there's no harm in trying, but it would be nice to repeat it. I think anything that would prevent that high vapor pressure deficit scenario from arising is gonna be a benefit as well. So like I was saying with the incubator, how they could kind of like keep the humidity high on their own. Um, and that's actually that Russo study that I referenced in the beginning that was looking at humidity. That's what they were testing was like, are there different shipping boxes that might be better? Um, I don't have any specific recommendation apart from we should maybe as an industry consider how to water bees during shipping. Where can I go watch this presentation again? Pat will answer that one. Michael, have you brainstormed with queen breeders regarding mechanisms to provide water in transit? Um, uh, well, there's the watering trough that I built. It's like a double baffled watering trough that does a pretty good job with those JZBZs. I can tilt them getting close to vertical without water coming out of that stuff. Um, People, for understandable reasons, are really hesitant to ship water with queens because if the water spills, you have a big mess on your hands, like the insects are all wet. Uh, so who have I talked to about this? There's Vivian Butts, there's Albert Robertson, and then I happened to be around some big queen breeders in California, um, who said they would mist their queens more before shipping. So no, I haven't really communicated this to queen breeders that well. Pete Foster, sponges. Yeah, sponges are an option too. All those, ooh, this is okay. This is something I should have mentioned prior to now. Uh, in the US, you can ship bees, you can ship queens with loose bees. And so when you're shipping queens with loose bees, you can put a sponge in there and then the bees can like the workers can drink water from the sponge and then go to the queens supposedly and like attend to the queens. And so maybe that's a way of getting around it in the US. However, in Canada, we're not allowed to ship queens with loose bees. They have to be shipped naked. So shipping naked is like we have 5 attendants in a cage and that is it. And so the sponge option isn't really an option in Canada, or if you're shipping to Canada. So Frank Lindsay again, I don't know how to say it, Woike, found that queens introduced in plastic cages had nowhere to get away from bees and had tarsal pad damage, so they were superseded after a few cycles of brood. His solution was to cover the cage with tape to give harborage and prevent bees from nibbling at their feet, just like the California cages do. Yeah, so I'm aware of that work actually, and I think the JZBZs, they have the bottom of the, and Frank, you might disagree with me about the JZBZ cages here. Like maybe you just don't like JZBZ cages. They have like a part to them that is designed to prevent that, I believe. So the queens can kind of like hide out and chill out. So when you look on here, I think that's why this whole bottom part here is solid. So the queens can go up and get attention. They can kind of walk on these solid bits, but they can hide out so their tarsal pads aren't chewed on. So like, I think the JZBZs are probably okay in that way. And then share a link to your YouTube page. So yeah, are there any other questions? I think.
All right. Well, thank you so much, Tracey, for doing this. All right. Well, thank you again.
Sure.
Good
Yeah.
night.
Yeah. Good night.